my name is François Maréchal. So I'm professor in EPFL, Industrial Process and Energy Systems Engineering Research Group, where I'm located in the campus of EPFL in Valais. Today I'm going to explain you a little bit what is the meaning of transitioning our society towards net zero. And this is in fact going to you have to recognize that we are living on a heating Earth. There are a lot of signs that tell us that the Earth is really heating. So the 12 last months, the ocean, which are taking the 90% of the Earth's heat imbalance, have been showing very high temperatures and records. So the question is there a thermostat there, right? So, and well, we can say that the thermostat is offered by a lot of technologies. So there are all my colleagues who are proposing to capture carbon dioxide, to promote hydropower, nuclear, wind, solar. So there are a lot of people who are developing technologies, and unfortunately, you cannot just buy one technology and decarbonize. You have to think system, and thinking systems means that we have to look at the system. Perhaps starting by understanding what are the needs of the people. So what are the products that they need? What are the services, being the comfort, the data, the mobility that they need, as well the way they need those services, like the security of supply. So it means that we have to understand the people, and then we have also to understand where are our resources. And as we do not have to use any more the fossil resources, we have to find new ones that are around us. But we have to know when, where, and how much we have. And then we have to activate the technologies. So it means, and activating the technologies means that we have to decide which kind of technology we are going to buy, at which size, for which purpose. And I would say that the question is more or less, we have to choose the technologies, we have to size them, we have to connect them, and then we have to be able to operate them. And if we have to take those decisions, then we have to have metrics that allows us to take the decisions. And I will name them the sustainability metrics, because we would like to be living in a world that will maintain its habitability, I would say. And therefore, we will have not only to take decisions about economic criteria, but also the value that we give to our environment, being an environment where the well-being will be important, where the quality of the environment will be important, where the health of the people will be important. And we have also to integrate into our decisions the planetary limits. So we have to recognize that we are impacting the world in which we are living. An important dimension is the time we will phase out the fossil use is that we will have also to look at more circularity. It means thinking about transforming waste into new products, or transforming the energy of the waste into energy services. And this also introduces a new nexus, which is the wastewater energy nexus, that needs to be integrated in the system that is in front of you. And as we care about the future generations, we also have to look at the greenhouse gases balance, which results into the need for CO2 sequestration. So this is the problem that is stated. Now we have to see how we are going to do it. So today, with the technologies that we have, we can imagine of having a virtual system that is going to be able to know what are the data that are available and the innovations that are available. And we can imagine that the computer can assemble those solutions to show us what are the good ones, to quantify which are the impact of those decisions to be taken, and activate the capital. So this is a concept of a digital twin that would show us where to go. And this is where we are doing research in EPFL. So we are working on integrating the innovation into databases, into models that allows to show how the technologies can be interconnected one and operating one with the others. We are able to use those computers and those models in order to generate a list of good connections. So choose the technologies, size them, connect them, and show how they can be operated. And this will result into a list of options that can be then proposed for an interpretation and an evaluation. So we are going to measure for each of the generated configurations the performance in terms of economy, in terms of thermodynamics, in terms of environmental impact and sustainability, to finally help the people taking decisions. So, and the decisions will be, by definition, a compromise between different criteria, where we would like to know what are the difference, what is the risk, what is the impact of those configurations that we can generate. So the digital twin approach allows us to see what are the good options. Now the question is, how do we implement it? And I would say start by a simple example. So typically you know where you are and you know where you would like to go. And something that would be really nice is that if you are informed about with the same cost, with the same amount of money, can you decrease still the emissions, or with the same level of emissions, is there a cheaper solution than the one that you are thinking is being the best? And so the idea here is really to be able to take those decisions. And for doing this, then we have to go into a systemic analysis. And the systemic analysis is going to look for different domains. So for example, the human system domain, what are the technologies that have to be activated, how they will be interconnected into the infrastructures, and how this will appear for the different stakeholders. So if I'm taking the city, you will have to look at the buildings, but at the same time, the PV panels, the heat pumps, the shopping malls to be integrated with the electric vehicles that will come, with the data centers. And you can see that I can start doing a brainstorming. And if I am the utilities, if I am the representative of the authorities, or if I am a simple citizen, I will see that I will probably have different preferences. So the goal is to be able to assemble in a system the different options. And this is what we try to do by activating, on the one hand, thermodynamics. So Carnot has shown us the way. So Carnot is going to say, so first you have to be sober. And then you have to get the energy from the environment as much as possible. And then the rest needs to be converted. And this results into a building that has PV panels on the roof, that has a heat pump inside the building, that has batteries, that has also a hot water storage tank. So why do I need batteries? Why do I need tanks? Is because the sun is not shining at the time at which I'm going to use the services. And this is then requires a coordination. So there will be time where we'll have the energy that is available for my needs. There will be time where I will have to import energy, and therefore I will connect the buildings to the grid. But there will be time at which I will have an export, and therefore I will have to profit from the fact that someone else will probably need the excess of energy that I have produced on my roofs. And this is going to need the integration of, or the coordination. We need an integration with intelligent systems that are going to make the link between when the sun is shining and when the people take a shower, to finally be able to operate the system and maximize the self-sufficiency. When I'm doing this, so you can see that I have integrated a lot of competencies to be able to do this, from the data scientists to the technology developers. Then I will be able to show how much it will cost in the future to be heated as compared to today. And when I'm saying today, so this was the results in 2001. And in 2001, the system was already cheaper than today to heat the people, but with a big difference. A huge investment to be made and a low amount of energy to be bought. On the other hand, if now I believe that I rely on Putin, so this is the security of supply, you can see that it is even better to go towards the renewable energy, because it will be even cheaper to be heated in the Putin era. So the reason for this is that I'm going to get much more value out of the excess of electricity that I'm going to supply to the grid. So this is interesting because now you can see that I have a system that is telling me, okay, at the end, you have to move towards a new decarbonized systems with 90% CO2 reduction emissions. And of course, I can be really smart. So not only I will integrate a fuel cell, a heat pump, sorry, but I will renovate my building. I will buy PV panels. I will buy an electrical vehicle. I will also probably integrate a data center into my building. And by combining all those elements, which corresponds all to my needs, what I realized that for the services, so here it's the mobility, the comfort in the buildings, the data supply, I'm able to have a system that is much cheaper. So here you can see that I have reduced the cost, and those are the cost of with the prices of today by two-thirds. So I'm going from 100 to 30 Swiss francs. So, and this is even more important if instead of being an individual, I'm looking at an overall a community, like a district. When I'm looking at the district, I need to know who is who and what are the different usage and opportunities there, how I can interconnect the buildings once with the other. But the conclusion of this is that at the same feeding and feed out prices, in this case, we were able to show that if the people start to buy together the equipments, they will buy more PV panels, they will reduce more the CO2 emissions because they will need less from the grid. And they will finally recognize that there is an interest to work together. Something which is then important also is that I'm not just looking at the electricity, I'm going to look at the multi-energy system. Carnot is telling me that you have to change the good sources, and this is what we are going to do. So with a district heating system, we can harvest the heat where it is available, being in the environment or being as waste heat, and I can even convert the waste heat that I have into electricity before distributing the heat to the buildings. When you can see there is that I'm integrating a system by in a multi-energy way, and the consequence is that I can make cities much more energy efficient and reduce their energy needs. The study we have made in the city of Geneva, so this was for the city center of Geneva, are showing that we can reduce by 16% the electricity consumption just by integrating the system with the right infrastructure. Something which is also important here is that I still need to do the import and the export. And that's where the technologies are going to come into play. And this is the second dimension of the systemic analysis, is integration of technologies, being batteries, fuel cells, electrolyzers, but also other types of resources like the biomass. And at the same time, it will introduce the need for or the opportunity for CO2 capture and storage. And something which is also important there is that each time I'm going to connect to speak about technologies, I will ask myself, how does it connect to the infrastructure, being the power systems or the gas infrastructure. And when I'm speaking about the gas or the power infrastructure, I'm going to start speaking about the energy management and the large-scale energy management. So when do I activate, for example, the hydropower? Just some comments about the technologies. Fuel cells can be used in order to supply the electricity that is missing. Fuel cells allows also to do CO2 capture. So it means that if I have a storage tank, then I can store the CO2. And fuel cell I'm going also to supply heat. So now if I can reuse the waste heat, and I have shown you that with the district heating system integration, I can harvest the waste heat, then I will be much more efficient in supplying the needs with the methane. But reversing this system is also possible. And in this case, I will use the electrolysis. So I'm inverting the voltage of the system. So instead of producing electricity, I'm going to consume electricity. Instead of producing carbon dioxide, I'm going to reuse the carbon dioxide, and I will produce methane. And if I'm now integrating this technology in the system, then I will have a system that in the winter is going to consume natural gas to supply the electricity for my heat pumps, collect the heat and harvest the carbon dioxide that will be stored, wait for the summer where this carbon dioxide will be again reconverted into methane by using the excess of electricity that I have on my roofs. And by doing this, then I will also already be quite efficient. But at the same time, I will realize that the people do produce waste. And part of the waste that the people produce is organic waste. And if I now activate technologies that allows to convert the energy value of the organic waste into useful services, I can, for example, activate biomethanization or gasification techniques that will produce methane out of my organic waste. And the byproduct will be carbon dioxide. And I know how to deal with the carbon dioxide. So I'm going to propose now systems that are not only going to convert the energy of the biomass into stored energy in form of methane, for example, but I will have also the opportunity of converting the byproduct, which is carbon dioxide, into an additional amount of methane, provided that I have electricity available on the grid. So now I have a seasonal storage device that is integrated to my system. Something which is important is that it's not necessarily written that I have to use the total amount of CO2 that is co-produced by the conversion of biomass. I have also the possibility of converting this additional amount of carbon dioxide as a biogenic carbon that can be sequestrated, creating negative emissions. And I'm speaking about methane, but it can also be other type of fuel. It can be the liquid fuels, and especially the one that can be used in the airplane, so the kerosene, which will be then biojet e-fuel. So at the end, I will have to understand that the system will then be 100% integrated with even the capacity of becoming negative, a source of negative emission. And I will close the energy balance of my system, looking at not only the city and its needs, but dealing with the seasonal management. And you can see here that I have added the industry that is defined as a heat source that can then be used to supply in a more efficient way the heat to the city. And therefore, I will have to have a very big integrated system with distribution, with management, and introducing the gas to power and the power to gas conversion. This, of course, requires an investment and requires the harvesting of the local energy resources inside the system. But we have been able to demonstrate that cities can be 100% autonomous with this kind of approaches. There is something which is important here, is the industrial processes. So industrial processes is more or less 20% of the consumption of the society. And we have to look at this dimension. We can, when we look at the industry, first we have to understand the needs. So what is the needs of the processes to in form of energy? Then we have to integrate the process innovation. Then we have to integrate the efficiency that can be in form of heat recovery or heat pumping, but also the integration of renewable energy resources in the processes. And then we have to recognize that a process is just one element of the full system. So it means that we will have to investigate how the industry can be used as a tank for the electrical power grids, how the industry can be used in the waste management and the circular economy, and how the industry can be used as a way to harvest carbon dioxide that can then create the negative emissions that are needed to close the energy balance. So when we do this, then you will have to activate a systemic analysis of one industrial process. And what I would like to show you here is that the process is an element in the system, is going to see a lot of different types of grids, local grids and big grids, is going to see on the one hand, the environment, so like the resources like biomass and wood, for example, but we'll also see the cities. And at the end, we will have to be able to do a systemic analysis that will allow us to understand where and how much energy we need, where the technologies can be used in order to reduce our energy needs and be more efficient in using this energy and using the materials in the conversion of the raw materials into product in the industry. Identify how we can valorize the heat that is available and that is processed by the industrial processes to finally be able to say how can we use the energy, the renewable energy sources as a way to supply the energy needs of the industry. And what you can see here is that it's not only the one that is locally generated, it can be also coming via the grids. In addition, we will have to recognize that due to the interconnection of the industry with the neighbors and with the main grids, the industry can become a battery for the main energy systems. And at the end, we will have also to recognize that the industry has to be integrated into the waste or the material flows of the city, and as well be a source for the waste heat that cannot be valorized inside the industry as a source for heating the people in the cities. So by doing this, then I have to really generate a holistic vision. Something which is also important is that the time I'm connecting my industry to the rest of the world, I need to know the rest of the world. So it means that I need to be able to understand at the systemic level for the whole territory, what will be the electricity to be stored, for example. Okay, and due to this, I need to understand the needs of the people. I need to understand how they are going to change their, on the one hand, the needs, how much they need. So, and this is related to the sovereignty, but also the way they are going to use the energy that they are going to use to supply their energy needs. And this means also to have a good understanding of the spatial integration. So it means that I will have to be able to know where are the resources, I will need to know where are the needs, and I will have to understand then how are the technologies that will be activated. If I identify at the level of the system which are the technologies that are activated and which are the storage tanks that will be activated at the systemic level, then I will be able to tell the industry at which time they will need to store, they will have cheap electricity to store, and at which time they will have the expensive electricity that someone is ready to buy. But at the same time, I will also know that the people need heat or not. Okay, and therefore I will be able then to measure, activate all the technologies and measure the impact with the holistic approach, which means that I will be able to identify, to activate all the sustainability metrics that measures the impact of all the decisions I'm going to take, but also the financing, the financial value of all those flows that will be exchanged between the different people in the system. So it means that I will have to create maps where I will know what are the needs, what are the different resources. Then I will be able to activate all the options that I was generating for the district, for the industry. And then I will be able to give what will be the future and how we can make the transition from the present situations towards, for example, in this case, a net zero options where for an independent Switzerland that is only using the local resources to feed the needs. So the conclusions. There is one way to stop the thermostat, is not to use energy and go back to the caverns, but there is another way, and this is what is our mission in EPFL. On the one hand is to work on the innovation transfer, so not just innovations, but integrating the innovations into the energy systems. We believe that the use of advanced techniques like the digital twins concepts allows us to show where are the possible options. And I'm really speaking about with the S. So there are more than one options. and we have to be able to compare them and to understand what are the metrics that needs to be used to take the decisions. In addition, and this is the mission of this training program that Jean-Marie is going to present, is the knowledge transfer. So we know how to do it, yes, probably, but it's important that all the engineers and all the people, the citizens, knows how to do it, are informed about the different options, so that they are not blocked in just one option. And therefore, we are proposing, on the one hand, of course, the training to our master students, but as well a continuing education program that allows to activate this knowledge, so that the engineers will be who are responsible for the energy transition will do it in an efficient and well-informed way. So those are my conclusions. So now I'm going to pass the word to Jean-Marie, who is going to present the program that we are proposing for the continuing education.